Welcome to Edisla. Humanity stands at the edge of a new frontier. Colonizing other worlds is no longer science fiction, but a real possibility, a necessity for the future of our species. The Earth faces increasing challenges, and establishing a presence beyond our planet offers a safety net for humanity. As we take our first steps into this vast new frontier, two celestial bodies stand out: the Moon and Mars. The Moon, our closest celestial neighbor, has beckoned humanity for millennia. Mars, the red planet, has captivated our imaginations with its potential for life and its Earth-like qualities. Both the Moon and Mars offer unique advantages and challenges for colonization. To fully grasp the complexities of this choice, we must delve into a detailed comparison of their characteristics and the challenges they pose. The Moon presents a significant advantage over Mars due to its proximity. A one-way trip takes about 3 days, making frequent missions feasible. Communication with Earth is near real-time, crucial for early colonization stages. The Moon's proximity also allows for rapid emergency assistance, ensuring the safety of a lunar colony. Mars presents a more formidable challenge in terms of distance. A one-way trip to Mars would take an estimated 6 to 9 months. The long distance means communication with Earth would be significantly delayed. A Martian colony must be self-sufficient and capable of handling most contingencies independently. The Moon's proximity makes regular resupply missions from Earth feasible. Mars would require a more self-sufficient approach to resource management. Communication with a Martian colony would necessitate asynchronous methods due to signal delay. This would require new technologies to facilitate effective information exchange between Earth and Mars. Gravity plays a crucial role in shaping our physical form. Prolonged periods of low gravity can lead to muscle atrophy and bone loss. The cardiovascular system is also affected, leading to potential health issues. Understanding these effects is paramount for long-duration missions and permanent colonies. The Moon's weaker gravity poses unique challenges for human health. Accelerated muscle and bone loss are primary concerns. The cardiovascular system may suffer due to reduced workload. Shielding from radiation is crucial for any lunar habitat. Mars offers a more forgiving environment for human physiology. Its higher gravity could slow down muscle atrophy and bone loss. The cardiovascular system would benefit from the stronger gravitational pull. However, the long-term effects of living in Martian gravity are still unknown. The Moon presents a stark contrast to Earth with its scarcity of resources. Water, ice, and lunar craters could provide essential supplies. Lunar regolith contains oxygen and silicon for life support and energy. Helium-3 on the Moon could be a valuable resource for future fusion reactors. Mars possesses a wealth of resources that could support a self-sustaining colony. Water, ice, and carbon dioxide are essential for sustaining human life. Martian soil contains minerals needed for agriculture. These resources make Mars a compelling target for long-term colonization. The goal of colonizing other worlds is to create self-sustaining settlements. The Moon might initially rely on resupply missions, but needs to utilize local resources. Mars offers a more promising pathway to self-sufficiency with its resource endowment. Achieving self-sufficiency will require ingenuity, innovation, and collaboration. The Moon, devoid of a substantial atmosphere, stands exposed to the full brunt of space's fury. Unlike Earth, with its life-sustaining blanket of air, the lunar surface is a harsh and unforgiving environment, bombarded by radiation and micrometeoroids, subject to extreme temperature swings, and lacking the pressure regulation we take for granted. The absence of an atmosphere means that the Moon has no natural shield against the Sun's harmful radiation. This includes ultraviolet, UV radiation, which can cause severe sunburn and skin cancer, as well as X-rays and gamma rays, which can damage DNA and increase the risk of various health problems. Beyond solar radiation, the moon is also exposed to cosmic rays, high-energy particles that originate from outside our solar system. These cosmic rays can penetrate deeply into matter, posing a significant threat to human health and damaging electronic equipment. The lack of atmospheric pressure on the moon also presents challenges for human survival. Without the pressure exerted by an atmosphere, liquids boil at a much lower temperature. This means that water, essential for life, would rapidly evaporate on the lunar surface. Mars, while possessing a thin atmosphere, offers a modicum of protection compared to the moon's stark nakedness. Though far less dense than Earth's atmosphere, this tenuous veil of gases provides some shielding against radiation and helps to moderate temperature extremes. Mars's atmosphere, composed mainly of carbon dioxide, is about 1% as dense as Earth's. This thin atmosphere is sufficient to slow down and break apart some incoming meteoroids, providing a degree of protection against these celestial projectiles. The Martian atmosphere also absorbs some of the sun's harmful UV radiation, reducing the amount that reaches the surface. However, it's important to note that the level of UV radiation on Mars is still significantly higher than on Earth, necessitating protective measures for human explorers. While Mars's atmosphere offers some benefits, it also poses challenges. Its low density means that it doesn't retain heat well, leading to significant temperature swings between day and night. Additionally, the thin atmosphere provides minimal resistance to wind, allowing dust storms to engulf the planet, potentially disrupting operations and posing risks to human health. Colonizing the moon or Mars will require overcoming the challenges posed by radiation and the lack of a substantial atmosphere. This will necessitate innovative engineering solutions to create habitable environments that protect humans from the harsh realities of space. One approach to radiation shielding is to build habitats underground or within natural features such as lava tubes or craters. These subsurface structures would benefit from the natural shielding provided by layers of rock or regolith. Another approach is to develop advanced materials that are highly effective at blocking radiation. These materials could be incorporated into the construction of habitats, spacesuits, and vehicles, providing a portable shield against cosmic threats. In addition to physical shielding, active radiation mitigation techniques could be employed. This might involve generating artificial magnetic fields around habitats, or using advanced filtration systems to remove harmful particles from the air and water supply. The moon, tidally locked with Earth, presents a unique challenge for human adaptation: its protracted day-night cycle. A single day on the moon lasts nearly 15 Earth days, followed by an equally long lunar night. This extended cycle has significant implications for future lunar inhabitants. The prolonged periods of daylight and darkness could disrupt sleep patterns and overall well-being. Solar power would be unavailable during the long lunar night. The extreme temperature swings between day and night further complicate matters. In contrast to the moon's languid rotation, Mars spins on its axis at a pace remarkably similar to Earth's. A single rotation of Mars, known as a sol, takes approximately 24.6 hours, just slightly longer than an Earth day. This near synchronicity with our planet's day-night cycle offers a welcome familiarity for potential Martian colonists. The Martian sol, with its close resemblance to an Earth day, would ease the challenges of human adaptation. Our circadian rhythms, attuned to a roughly 24-hour cycle, would require minimal adjustment to synchronize with the Martian day. This would likely result in better sleep patterns, improved hormone regulation, and a reduced risk of health problems associated with disrupted circadian rhythms. The Martian sol also offers practical advantages for mission planning and operations. Solar power, a key energy source for a Martian colony, would be available on a predictable cycle, simplifying energy management. The relatively short transition between day and night would also reduce the strain on thermal control systems, making it easier to maintain comfortable temperatures within habitats. While the Martian sol provides a familiar rhythm, it's important to note that Mars does experience seasons due to its axial tilt, similar to Earth. However, these seasons are more extreme and longer than their terrestrial counterparts due to Mars's elliptical orbit and thin atmosphere. While the Moon and Mars both present challenges for human habitation, their climates differ significantly. The Moon experiences extreme temperature swings due to its lack of atmosphere. Mars, with its thin atmosphere, has less drastic temperature fluctuations. Mars's thin atmosphere helps distribute heat, moderating its climate. However, Mars is still cold and prone to planet-wide dust storms. Pursuing a dual-pronged approach, establishing a presence on both the Moon and Mars offers the most compelling strategy for ensuring humanity's long-term survival and prosperity. This strategy is not about choosing one destination over the other, but recognizing their complementary roles. The Moon serves as an ideal stepping stone for developing technologies and infrastructure. Mars represents the ultimate goal, a second home for humanity, with the potential to support a thriving civilization. By establishing a presence on both, humanity creates a safety net against unforeseen catastrophes. Beyond the imperative of survival, colonizing the Moon and Mars opens up a treasure trove of scientific and economic opportunities, pushing the boundaries of human knowledge and driving innovation in countless fields. The Moon, with its ancient surface relatively undisturbed by geological processes, offers a unique window into the early history of the solar system. Lunar geology can provide insights into the formation of planets, the bombardment phase that shaped the inner solar system, and perhaps even clues about the origins of life itself. Mars, with its evidence of past liquid water and potential for harboring microbial life, presents one of the most compelling targets in the search for extraterrestrial life. Exploring the Martian surface and subsurface could answer one of humanity's most profound questions. Are we alone in the universe? Beyond pure science, the Moon and Mars offer vast resources that could fuel future economic growth. The Moon's helium-3, a potential fuel for fusion reactors, holds the promise of a nearly limitless energy source. Mars, with its abundance of water ice, carbon dioxide, and minerals, could become a hub for resource extraction and manufacturing, supporting both its own burgeoning population and future spacefaring endeavors. As we've explored the distinct characteristics of the Moon and Mars, it becomes evident that both celestial bodies offer compelling reasons for human colonization. The Moon, with its proximity and accessibility, serves as a practical stepping stone, a proving ground for the technologies and strategies required for venturing further into our cosmic neighborhood. Mars, on the other hand, beckons with the allure of a more Earth-like environment, a planet with the potential to become a second home for humanity. Choosing between the Moon and Mars is not an either-or proposition. Instead, a dual approach offers the most comprehensive strategy for securing humanity's future. This two-pronged approach mitigates risks, diversifies our species' portfolio across multiple worlds, and maximizes the scientific and economic opportunities. Colonizing the Moon and Mars is not merely an exercise in scientific exploration or technological prowess. It's a testament to the enduring human spirit, our innate drive to explore, discover, and push the boundaries of what's possible. It's about securing a future where humanity is no longer confined to a single planet, a future where we can spread our wings and reach for the stars. The challenges of colonizing other worlds are undeniable, from the harsh realities of space travel to the complexities of establishing self-sustaining habitats in alien environments. Yet throughout history, humanity has consistently risen to meet seemingly insurmountable challenges, driven by our ingenuity, our resilience, and our unyielding belief in a brighter tomorrow. The endeavor to colonize the Moon and Mars will require a global effort, a collaborative undertaking that transcends national boundaries and unites humanity under a common goal. It will necessitate the pooling of resources, the sharing of knowledge, and the fostering of international cooperation on an unprecedented scale. This is not just a mission for astronauts and scientists, it's a call to action for all of humanity. Engineers, architects, doctors, educators, artists, and dreamers from all walks of life will be needed to contribute their talents and expertise to make this vision a reality. As we stand on the cusp of this new era of exploration, the possibilities seem limitless. Colonizing the Moon and Mars is just the beginning. The knowledge and technologies developed will lay the foundation for more ambitious endeavors. We may one day mine asteroids for resources, build space stations that orbit distant planets, and perhaps even discover extraterrestrial life. The colonization of the Moon and Mars represents a pivotal moment in human history, a defining chapter in the story of our species. It's a story of courage, ingenuity, and an unyielding belief in human potential. The future awaits, and it belongs to those who dare to dream big, a future among the stars.